Bronwyn is standing on a scale in a lift. Her mass is 56 kilograms. If the lift is moving upwards at a constant 3 meters per second, this is the important thing. It's a constant velocity, therefore no unbalanced forces. If there are no unbalanced forces, then it's going to be as if she was standing on the floor, on a stationary floor with nothing weird happening whatsoever. Want to know what's the reading on the scale? Well, the reading on the scale, no one said it was a Newton calibrated scale, so her mass is still 56 kilograms. So the reading on the scale is A. In which of the following cases do balanced forces act on an object? Balanced forces, a lift is starting upwards from the ground. That means it has to be accelerating, because otherwise it would just stay on the ground if it wasn't starting off by speeding up. A bullet is moving along the barrel of a gun after the gun is fired. It turns out that the bullet must be slowing down. So that is not constant or balanced forces. An aeroplane is flying horizontally at a constant velocity. Constant velocity always implies balanced forces. And an athlete leaving the starting blocks, that is also speeding up or accelerating. So if there's a change in velocity, I've got acceleration. If I have acceleration, I will have an unbalanced force or a net force somehow acting on the object. A girl weighs herself on a Newton calibrated scale. The scale shows a reading of 500. With what force does the girl attract the earth? Well, the earth is attracting the girl with 500, which means that the girl will be attracting the earth with exactly the same magnitude force. It is a Newton's third law example. A 50 kilogram student stands on a bathroom scale in a lift. If the lift reads 40 newtons, what is the lift probably doing? Well, if she's 50 kilograms, she will have approximately 480 newtons. Okay? This is less than 480 or 500 or that ballpark. I mean, you don't even have to do the calculation. It's 50 times 9,8. So it means that she is feeling lighter. If she is feeling lighter, it means that the lift must be accelerating away from her, which means it is accelerating downwards. If she felt heavier, it would be coming up. She would have the same mass, in other words, around 500 newtons, 480 newtons if it was stationary, or if it was constant velocity. But in this case, she's lighter, so it is accelerating downwards. A mass of 2 kilograms is suspended from a spring scale. Under what circumstances will the reading on the scale be less than 19,6? When the scale is being what? So what I need is normally 19,6 would be going down. And if I want this to read less, I need to be coming against that in some way. In order to get a lower reading on that, definitely nothing constant velocity. And then what we're going to do is, if I accelerate this downwards, then it will exert an equal but opposite upward force, in other words, minimizing that number. So it is going to be, when I accelerate that downwards, that the scale is going to be lighter. A lift hangs on a steel cable. The tension in the cable is greatest when? Now, normally I have a lift and I have a tension. If I have a weight and I have got a force resultant going upwards, and if the lift is actually accelerating upwards, then I am going to say force resultant is equal to the tension minus the weight. Big force minus little force. So let's work out the tension then. Tension is force resultant plus weight. If it hangs still, obviously that's not going to be a maximum situation, and constant velocity is not a maximum situation. Let's try downwards. Force resultant, I'm accelerating downwards, so the lift is moving down. If the lift is moving down, I'm going to land up with weight being big and tension being small. So if I now write what is the tension, I find that it is the weight minus the force resultant. So you can then see quite clearly that the tension is biggest when we were accelerating upwards, because we have to make sure that we are moving this lift up and working against weight. Stephen is standing on a Newton calibrated scale in a lift. His mass is 65 kilograms and the lift is accelerating upwards at 1,5 meters per second squared. As the lift pulls upwards, I feel heavier. And I can do a whole Newton's third law round and about, but actually lets me just imagine myself in a lift and I feel heavier. So I'm going to take that I would normally be exerting a downward force of 65 times 9,8, and I'm going to add to that 65 times 1,5, which is the equal but opposite force against the upward motion that there is now. The man exerts a downward feeling onto the lift, and therefore my reading on the scale is going to be 734. Stephen is standing on a Newton calibrated scale. His mass is still 65 and he is accelerating upwards at 1,5. What would happen if the lift started free falling? Free falling is a downward acceleration, and downward acceleration you subtract. You feel lighter when the lift is accelerating downwards. So it's going to be 65 times 9,8 minus 65 times, what is the gravitational acceleration if I'm free falling? 9,8, and that is 0 newtons. Nazneem is standing on an elevator which is accelerating upwards in a building. If her mass is 45 kilograms and the lift's acceleration is 2,2 meters per second squared, calculate the magnitude of the force exerted by the floor onto Nazneem as a result of the acceleration of the lift. So, if the lift is pulling upwards, the upward force onto Nazneem, just because of the acceleration, not the total force, is going to be 45 times 2,2. And that turns out to be equal to 399. The next one is calculate the magnitude of the force exerted by Nazneem's shoes onto the floor. Well, Nazneem is going to exert an equal but opposite downward force that is also equal to 99. So that's the reaction force, plus she already had her weight, which was 441, which is 45 times 9,8. And therefore, her shoes exert both those forces onto the ground, and we land up with an answer of 540 newtons. A boy of mass 67 kilograms stands on a lift in a bathroom scale calibrated in newtons. What will the reading on the scale be if the lift is stationary? If it's calibrated in newtons, you just need to take 67 and multiply it by 9,8, and you land up with an answer of 656,6 newtons. I mean, you don't have to give it a direction at all. Same boy, 67 kilograms. What would the reading be if the lift moves upward? Constant speed means no unbalanced forces, and therefore it's just like being on the ground, and therefore it's going to be 656 newtons again. Now we have the same boy, and what if the lift was pushing up, accelerating upwards on him at 2 meters per second squared? He would push downwards equal but opposite additional force, so it would be the 656,6, plus he would feel heavier to the tune of 67 times 2, which is going to be 134, and when I add the two together, it's 790,6 newtons. C. That same boy, what would happen if the lift was moving downwards at 3 meters per second squared? Now he would feel lighter, so it would be 656,6 minus 67 times 3, this new acceleration, which happens to be 201 newtons. When I do that subtraction, I land up with 455,6 newtons. Finally, we've got the same boy. What would the reading be if he was in free fall? Free fall is like super duper downward acceleration, minus 67 times free fall acceleration, 9,8, and I land up with C, which is 0 newtons.